an instant t naught such that the orbits in starting from A for instance t bigger than or equal to t naught are relatively compact. Okay, so this is true. Then you have very interesting result about omega of A. So the first thing is omega of A is also non-empty. In other words, there must be some element, okay, there must be some equilibrium point actually to which your solution to nonlinear evolution equation would converge actually. Okay. In general, this set can be empty. In other words, that it can't converge to anything. You know, it could be so because that in when we were considering, for example, the case that when the norm of U stays bounded, you have two possibilities. Either it does not converge to some, stays bounded but does not converge to solution, does not converge, solution of the nonlinear evolution equation does not converge to some specific function in X, or it may converge actually. So the omega limit set can be empty, can be non-empty. But if your A is non-empty and you have the relative compactness, then for sure your omega of A is non-empty. Not only it is non-empty, but it is compact. This is important, and invariant actually. And invariant. Okay, so in other words, S of t operated onto omega of A gives back omega of A. Further, if you have an additional assumption on calligraphic A, that further if A is connected, then along with being compact and non-empty and invariant, then the omega limit set for A is also connected. Okay, so a lot of terms from topology, so you have to be a bit vigilant. For this last fact, I'll just give you a hint, and you have to read it for yourself actually, the proof of the connectedness. Okay. So let's do the proof. Let's do the proof. Now, let's start with non-emptiness. Now, since calligraphic A is non-empty, so since calligraphic A is non-empty, so f of t operated onto A is non-empty for all times actually. Okay, for all times. In particular, you know, s of t for t say bigger than or equal to s is non-empty, and not only this is not, so if this set is non-empty, its closure is non-empty. In other words, E of S is non-empty. Okay, once again, since A is non-empty, S of t operated onto A would be non-empty for all times. Okay, starting from anywhere, say some S, and hence their closure would also be non-empty. because at least this set itself is contained in the closure actually. Okay, because the closure is the collection of, set is the union of set and its limit points. If the set is non-empty, the closure is non-empty for sure, and hence E of S is non-empty. And if the E of S is non-empty, obviously if you remember what was the definition for omega of A, definition of omega of A is the intersection of E of S. So if for each S, E of S is non-empty, so that this intersection is non-empty, and hence omega of A is non-empty. How does the compactness follows? Compactness follows. Now, what is given to us? If you consider, say, an S that is bigger than or equal to T naught, then E of S by definition or by the given fact is compact. Why? Because this set for any instant after T naught is relatively compact. That means that E of S is compact. Okay. E of S is compact. Okay. For each S after the T naught. Now, not only E of S is compact, but you can also treat this E of S for S bigger than or equal to all T naught, okay, or even for S bigger than or equal to 0 as a decreasing sequence of compact closed sets actually. Okay, so compact and closed sets. Compact and closed sets. Okay, and if you have such kind of compact, closed sets, which is a kind of a decreasing sequence of which constitutes a decreasing sequence, then from basic result of the topology, their intersection is also compact actually. Their intersection is also compact. Okay? So that's a basic fact from topology you have to recall from your stuff. Hence the intersection of such S, say bigger than or equal to E, bigger than or equal to S, which is bigger than or equal to T naught, E of S, which is omega of A, is compact. Okay? So you have such a result for intersections. So just open up Munkers and try to find the result that justifies that. And there is such a result actually. So why omega of A is compact? Because E of S is compact and the sequence is decreasing, and so that their intersection is also going to be compact actually. Alright? So this is what the case is. What is the next thing? The next thing is to show that omega of A is positively invariant actually. Okay? Is invariant actually. So omega of A is invariant. The invariance actually. In other words, I need to show that S of P operated on the omega, calligraphic omega of A is equal to omega of A. If you know from previous lemma, one intuition we already have it that S of P is positively invariant. So you know this already. So the key thing would be to show the reverse inclusion actually. that omega of A is also contained in S of t operating onto omega of A. So what I need to show that to show that omega of A is contained in here, I need to take what do you call say a phi from omega of A. So let's take a phi from omega of A. And I need to show that there is a psi in omega of A such that S of t operated onto psi give this phi, and that will prove that phi belongs to S of t operated onto omega of A. Now, what we know about phi, in order to find that psi, what we know about phi, that phi belongs to omega of A. So if phi belongs to omega limit set of A, then by definition there is a sequence as phi is in omega limit set of A, so there is a sequence Tn and phi n such that S of Tn operated onto phi n converges to what do you call phi. Okay, and obviously Tn goes to infinity. And from this we will like to construct what do you call construct construct a psi, okay, for which you have this. Now, as Tn goes to infinity, so there must be an instant when, say, Tn crosses t, any arbitrary instant t, fixed instant t plus t naught actually. Okay? So, you can find an instant n such that Tn is bigger than or equal to some t plus t naught where t is some instant after that. So in other words, no matter how far you go away from t naught, you will always have a term in a sequence that will be bigger than or equal to that instant after the t naught. Okay, so you can have this. And what we know about as assumption, what we know about say S of t. So if the Tn is bigger than or equal to Tn minus t is going to be bigger than or equal to 2, and then S of Tn minus t operated onto phi, okay, is going to be an instant that is after what do you call t naught. So this must be relatively compact. Now let me recall basically two definitions for the relative compactness, two equivalent definitions for relative compactness, which are true even in Banach spaces actually. So you're going to say that X is relatively compact if and only if, first of all, the closure of X compact in H, if and only if closure of X is compact in H norm, and this is equivalent to the case that if you take, say, any sequence xn in X, okay, if you take any sequence xn in X, you can always find a convergent subsequence of it actually. There is always a convergent subsequence, say xnk, and a limit in H such that xnk converges to what you call xn. So, as I said, a set is relatively compact if its closure is compact. So that's one characterization. But the other characterization of the relative compactness is also that no matter what sequence you take, that sequence must contain a subsequence that is convergent to some point in H, okay, the bigger space. Could be in X as well, okay, but should be in H. Now, what we know about this set, that if you take the t, any instant t after the t naught, s of t operated onto A is relatively compact. Okay, is relatively compact. So now you can treat this guy as a sequence in this set, in the relatively compact set. So I can treat this as a sequence in this relatively compact set, if this is given to me. Now, since this is relatively compact, so by this characterization, there exists a subsequence of Tn, which I am again naming Tn, so I am not writing Tn actually. Okay. Subsequence Tn of Tn, and a subsequence phi n of phi n. Okay, so I'm acting again, giving it a name, Tn, and a subsequence phi n. I can write Tnk and phi nk, but okay, so for the sake of simplicity, I'm again calling it phi nk, phi n, and a psi in H. Okay, and a psi in H such that S of Tn minus T operated onto phi n converges to this psi. Okay. Converges to this side. By the way, this also implies, by definition, since you have a sequence of times and a sequence of functions such that S of Tn minus T operated onto phi n converges to phi, so this also implies that psi is also an element of the omega limit set. Okay, it's an element in omega limit set. So, we have found one element in the omega limit set for which this must be true. So let's verify this. Let's apply S of t onto psi and let's see that whether you get phi or not actually. Okay? Whether you get phi or not. So now let's apply S of t onto psi. Okay? So I can say instead I can use another trick that, okay, if I apply say S of t operated onto S of Tn minus t operated onto phi n, okay, I know that by Famigor property I can write this as S of t plus Tn minus Tn, in other words that S of Tn operated onto phi n. Okay, this sequence we know by definition from the first fact that S of Tn operated onto phi n converges to phi. So this converges to phi. This converges to phi. And now let me find another limit for this sequence actually. And since this sequence is a sequence in Banach space, so there should be a unique limit, and hence the both limits should be equal actually. Okay, so what is the next thing? The next thing is that if you say consider S of Tn, next, if you consider S of Tn phi n, as we said, as above, I can write this as S of T operated onto S of Tn minus S of Tn minus T operated onto, say, phi n. So as n goes to infinity, I know that S of Tn minus T, S of Tn minus phi n converges to what do you call psi. It converges to psi. So I'm going to say that this converges to psi. So if this converges to psi and S of T is a continuous map, so it will map the convergent sequence onto the convergent sequence. In other words, S of T operated onto the sequence will converge to S of T operated onto psi. Okay? This will converge to the S of T operated onto psi. So now you have a same sequence which has a limit phi, and you have a sequence that has a limit, what do you call, S of T psi, and you are sitting in a Banach space. So this limit must be, what do you call, unique actually. Okay, this must be, what do you call, unique, and hence you're going to say that your phi is equal to S of T psi, and which shows that this is sitting in S of T, which shows that it's sitting in S of T operated onto omega of A, because I know that psi is also an omega of A. Okay, so this is what it's going to get. So what does this shows? This shows, and thus this shows that your S of T is, omega of A is invariant actually. So we proved the invariance property as well. Okay. For the connectedness, I am leaving the proof for you. So either try to do the proof of the connectedness for yourself, or try to, for example, read the notes and do that proof actually. Proof should not be difficult. Think about it. So if A is connected, okay, if A is a connected set, then and S of T is a continuous map actually. So we know that connectedness is a topological property. So in other words, if you take a connected space, and no matter how you continuously mold it, it will still be what do you call, connected actually. So if A is connected, ST of A is connected. And if the ST of A is connected, that means that E of S is connected actually. And hence you have to kind of show that the key thing that you have to show is that intersection of these E of S is also connected. And hence that will prove that omega of A is connected actually. Okay, so this is what roughly you have to do. As I said, that there is a lot of waving of hands, but you have to absorb these proofs basically. Okay, so let's collect what we proved so far. So we proved two basic properties of what do you call omega limit set. The first basic property is that it is always positively invariant. Okay, so it does not changes the space under the semigroup, action of semigroup. And the other thing is that under certain assumptions, very basic assumptions, okay, your omega limit set is a compact, invariant, and connected set actually. Okay? So these are the two important properties that we studied. And again, don't forget that what is omega of A? Omega of A, or the omega limit set, is the collection of the stationary points. Okay, we're going to see that these are, its element are basically equilibrium points, the stationary solution to the problems, to which the solution to the nonlinear evolution equation would converge in long run. So hence, you know the omega limit set, you know the points to which, you know, the solution of the nonlinear evolution equation converges at. So these are the two basic results that you have to keep in your head. The next is, I'm gonna move towards the section of the gradient system, the gradient flows actually. So what we want to do in these set of discussions, we're not going to consider the very generic, the big class of nonlinear evolution equation, but we're going to consider the class of the nonlinear evolution equations which are gradient flow. And you will see that most of the equations that you encounter, okay, like Schrödinger equation, heat equation, you know, all these equations are basically gradient flows actually, okay. And for when I'll put the result on the what do you call board, you will see that for the gradient flow, if you know that your flow, the solution to your problem is a gradient flow, nonlinear evolution equation is a gradient flow, then it is peanuts to find its omega limit sets, and hence it's peanut to find you know, the stationary, the equilibrium points of, it's peanut to find the long-term behavior of nonlinear evolution equation actually. Okay, so I'm moving towards defining gradient systems. Okay, let me start by defining first Lyapunov function. Okay, you might have heard this Lyapunov stuff very often, but if you are doing, for example, stability analysis for differential equation, dynamical systems, so the Lyapunov functionals are pivotal. So what's a Lyapunov function? Okay, so the Lyapunov function is a pretty simple function. I'll write a pretty abstract definition. So here's the definition. So let H be a metric space, be a complete metric space. Hence your Banach spaces and Hilbert spaces are included in this result, definition. Let H be a complete metric space, and S of T is a C0 semigroup as previously. Then a continuous function, okay, so a continuous function V that swallows the values from H, okay, and spits out the real number is called Lyapunov. Is called Lyapunov functions if it satisfies two properties. So a continuous function on a complete Hilbert space is called Lyapunov. It satisfies two properties, two basic properties. Number one,